Continuum hypothesis. The basic foundation for continuum hypothesis were laid by Leonhard Euler. Most of his concepts in fluid mechanics use the continuum hypothesis assumption. A fluid consists of large number of molecules in constant motion undergoing collision with each other. For studying fluid mechanics, often properties like density, velocity, temperature, and pressure are considered. In microscopic scales, the properties, especially density and velocity, might be discontinuous or discrete. In these cases, it is possible to study fluid mechanics considering the individual molecules as it is done in kinetic theory of gases or statistical mechanics. However, there is another way to estimate these properties, by simply considering the idea of average manifestations. To understand this idea, we need to know about certain estimates. Consider the molecular properties of air. A cubic centimeter volume of air at standard conditions consists roughly about 3 into 10 power 19 molecules. The standard conditions specified here corresponds to 273 Kelvin or 0 degree centigrade and at 1 atmospheric pressure, which is roughly about 101 kilopascal. A supercool electronic molecular counter that can count at a rate of 1 million molecules per second would require roughly about 1,000 years to complete counting all the molecules in just 1 cubic centimeter volume of air. Such numbers are so overwhelming and still not conceivable to human minds. Let us suppose we freeze these 3 into 10 power 19 molecules and rearrange them such that they are equally spaced, meaning they are separated from each other with the same distance. Then, the average molecular distance will be about 3 into 10 power minus 9 meter. But we are interested in molecules that are in motion and undergoing collision with each other. For these cases, it is necessary to consider what's called as the mean free path distance. A mean free path distance is defined as the average distance a molecule travels between successive collision with another molecule. Let me illustrate in detail. Let us assume that initially the molecules have been separated by the average molecular distance, which is roughly about 3 into 10 power minus 9 meters. The molecule indicated in red undergoes the first collision with the molecule indicated in blue. Let's denote this distance traveled before collision to be c1. On collision, the molecule bounces off and travels again a distance c2 before colliding with another molecule. This process continues over and over again. If we consider the sum of all these distances between each successive collision, that is c1 plus c2 plus c3 plus c4 and so on, divided by the total number of collision n, this average distance is termed as the mean free path distance. However, this illustrations of molecules colliding with each other in a very nice fashion is far from reality. This is to simply illustrate how the mean free path could be defined. At standard conditions, the mean free path distance is about 8 into 10 power minus 8 meter. That is, the mean free path is about 25 times the average molecular separation distance. This means a molecule has to roughly graze over 25 molecules before colliding with another molecule. If we start rearranging the molecules on one side of our cube, with the separation distance equal to the mean free path distance, we can roughly accommodate 15,000 molecules. This simply means that only an average 15,000 molecules can come in or out of this face of the cube at any moment of time. Let us downsize the cube dimensions to 0.1 times the mean free path length and compare the estimates with our original cube of length 1 centimeter. An estimate for density can be defined as the ratio of sum of the individual molecular mass within the control volume to the volume of the cube itself. It is considered in the limit of length L tending to some arbitrary length L0. Let me explain the appropriate limit of L0 later. In the smallest volume considered, there are roughly about 15 molecules inside the control volume compared to 3 into 10 power 19 molecules in 1 centimeter cube volume of air. The kinetic theory of gases estimates the fluctuations of density in terms of a root mean square value, indicated as rho dash or ms. This value for the downsized small cube is about 25%. This is understandable as there are only 15 molecules and there will be situations where there are all 15 molecules present and some moment there is nothing inside the considered volume. This affects the estimation of density as there will be considerable variation in the summed up molecular mass at different moments of time. But as the size of the control volume increases to 1 centimeter cube, the fluctuations decreases to 0.8%. Thus, the density does not change very much. That's a good news. But the question is, how does this fluctuation changes over the size range of L? This is an important question to be answered because we need a single estimate of density or any properties in this case that does not change with size of the control volume considered. Let us plot the term sigma m, sum of all the mass of the molecules for the given size of the control volume, divided by the volume in the vertical y-axis, with the length or logarithm of length of the cube considered in the x-axis. As defined earlier, the density is defined as the summation of mass over the volume for the limit L tending to L0. Plotting this term with the corresponding length parameter yields a plot like this. So, initially when the volume is small, say the length corresponding to the mean free path distance, there will be a significant fluctuation in the density as there are only few molecules inside the considered volume. As specified earlier, for length of orders less than the mean free path distance, the root mean square of fluctuations of density can be as large as 25%. But rather, when the dimension increases to the limit L0, the variation in density is steadier and smoother, meaning fluctuations are very small. But generally, instead of L tending to L0, we really should specify L tending to 0, meaning the limits are very small but not small enough compared to the mean free path distance. So, the right definition would require us to indicate L tending to 0 rather than L tending to L0. The x-axis here is specified in logarithmic scale in order to squeeze in the values that can vary from 10 power minus 9 to 10 power minus 2, that is, several magnitudes of variation. A small cautionary note though. When you consider the minimum size of the control volume, the liquid would have a smaller size in comparison to the gases. As in liquids, the molecules are closer compared to that of the gas. However, the concept of a mean free path distance is not valid for liquids.